Okay, so if we look at this question now, like I said to you guys before, if you see a table or a graph, do not read the question first. Look at the table or graph, study it, think about what it shows, and then answer the question. So I've had a look at it, and I've answered the question. So it says, calculate how much energy is wasted in 1 second by the compact CFL light bulb. Okay, so with these diagrams, what you got to realize is this downward arrow indicates what is wasted. Okay, so this is the wasted energy and this is the useful energy. Now if you didn't know that, you could work it out, because a light bulb, the useful energy of a light bulb is light energy, and that's there. So in this CFL bulb, the question is how much energy is wasted. Well, this is efficient energy and this is your total energy. So to work out the wasted is you do this, take away that, and whatever's left will equal this wasted energy here. So that's what I've done over here, and bam, 12 joules it is. Next, the question says, explain how you can tell that the CFL has a better energy rating. Okay, and why is that? Because number one, we've already worked it out. So this has a wasted energy of 12 joules. We worked that out over here. We could do the same for the halogen. The halogen, how much has it wasted? It's 20 to start with. Only 2 joules used as light. So 20 take away 2, the rest is wasted. It is 18 joules. So if you compare the wastage, the halogens clearly has more waste. Now here we can also do an efficiency calculation where you've got 2 joules of light divided by the total multiplied by 100. So for the halogen, so it's 2 joules of useful divided by the total, which is 20, multiplied by 100, that's 10%. And we do the same thing for here. So it's the useful, which is 8 joules, divided by the total, which is 20, multiplied by 100, which gives you 16% efficiency. So it's more efficient. Right, go on to the next page and wait for me there. Okay guys, as soon as you see this question, as soon as you see constant temperature and the word why, the answer is always the same. Why is it a constant temperature? Because the amount of power going in is the same as the amount of power going out. So the amount of power going into the system is the same as the amount of power going out of the system. Right, it's always the same. As soon as you see those trigger word, constant temperature and why, the amount of temperature going in is equal to the amount of temperature going out. Oh my god, what did I just say? I need to rephrase that. The amount of power going in is equal to the amount of power going out. So let me just write that. The amount of power going in to the system, it could be anything. It could be a pool, it could be your computer system, it could be anything with a constant temperature into the system, is the same as the amount of power going out. You get the point. Okay, I'm just going to pause it and draw a diagram and explain that a little bit more. So here are 3 different scenarios. If you look at scenario A, what you've got is you've got 100 watts going into a system and 100 watts going out. This is going to give you a constant temperature, this one here. Here, if you've got 200 watts going into a system, scenario B, 200 watts going in and only 100 watts going out, right? There's more power going in than there is going out. This one's going to be heating up. With this one here, if you've got 100 watts going in but 200 watts leaving, then with this one the object's going to be cooling down. Okay, so I'll see you on the next page. Have a go at the questions. Okay, so this is a bit of a strange question, but nonetheless the answer is 18, because if it's 18 at this point, which is really should be the hottest, and it's 18 at this point and it's 18 at that point, then really what we're going to say is that this must also be 18. The next part is, why do they use black? Because black is the best absorber of heat and you're going to get the maximum absorption of heat. Brilliant. See you on the next page. Not too difficult, this one. And this is based on Herschel's experiment, and we've already spoken about that a few pages ago, so I'm going to move forward. Okay, so I said the previous page had like weird results with all 18. I'm wondering, is that because I didn't read the question properly? Ah, yes, that's why. Oh my days, unbelievable. That is why I said it's weird, because I thought here they were measuring the temperature on the different spectrum, and I didn't expect it to be the same. However, it's not. You need to read the question, people. Read the question. It says the table has shown some of the readings on the thermometer in the shade. So yes, now I do see that the temperatures need to be the same. Okay, guys, here's a lesson for you. Read the bloody question. Right. Anyway, so now they're measuring the actual spectrum. Okay, and this one here, basically, if we look now, we're seeing what we expect, and we can write the conclusion down that number one, beyond, well, something clearly happening in this area, who knows what. Anyway, number one, that the P thermometer is going to be the hottest, and that's just beyond red, so that must be infrared. That's the first thing we can conclude, that P must be infrared, and it is just beyond the red, and it is the hottest. You can say similarly, another conclusion is that the S place has the coolest light, and it belongs to the violet section of the light. The question below that, it says, why did they put it at the shade? And this is what made me kind of suspicious. I was like, oh, when did they put it in the shade? So I looked back. I was like, yeah, that makes sense. So they put it in the shade for two reasons. Number one is to make sure that they both work, that all the thermometers work under the same conditions in exactly the same way. So to make sure they're all working correctly. And the other thing is to make sure that they all start at the same temperature, so that the temperature rise can be measured accurately, potentially. The final question is that overexposure to UV light can damage the eyes, in particular in really white, snowy areas where the UV light from sun rays can reflect into your eyes. That's going to cause you some damage. Okay, guys, see you on the next page. Answer the questions. This is an interesting question. So it says, 3 signals, ultraviolet, visible, and infrared, are sent to the surface of the moon. Which one arrives first? And the answer is that all of them arrive at the same time, because all of the electromagnetic spectrum that is raging March and invading Venus using X-ray guns, every single one of those travels at the same speed, which is 300 million meters per second. That's the speed of light. That's makes sense because light is one of the visible light is one of the parts of the electromagnetic spectrum. So every single one of those travels at exactly the same speed, which happens to be 300 million, or 3 times 10 to the 8, same thing, meters per second. It says describe one use of ultraviolet radiation. I've written UV beds because, you know, UV beds for tanning. The other one, the main one, is money security. Now here's my amazing £20. You all know that I'm amazing at drawing. The UV light comes in, it gets absorbed by the secret code, and as a response, visible light is reflected into our eyes, and we can see the secret code. So that's how UV security markings on monies works. See you on the next page. Okay, so yeah, this question here now, I just want to go through these facts here. So if you have a sound wave that is below 20 Hertz, we call that infrasound. If it's between 20 Hertz and 20 kilohertz, notice that kilohertz is the same as saying 1000. So if it's between 20 Hertz and 20,000 Hertz, this is normal sound. This is what the normal human hearing range is. If it's above 20 kilohertz, then we call this ultrasound, right? Humans cannot hear this, and we cannot hear that. This is our normal range of hearing. The other thing is sound waves are actually longitudinal waves. Okay, so they are waves that travel along the direction of travel, right? So let's have a look at the options. This one here, the microwaves, is the odd one out. Why? Because all of these are sound waves, except this one. This belongs to the electromagnetic spectrum. So that is raging Martians invading Venus using X-ray guns. This one is not longitudinal. It is transverse. Every single one of those EMS waves are transverse. Moving back to the question, it says if it's more than 20,000 Hertz, so above 20,000 Hertz, we call it ultrasound. So the answer is ultrasound. Yeah, this is about echolocation, so animals can use it, and human beings have learned to use it as well with sonar, so it's exactly the same principle. you let out this ultrasound high frequency waves. It reflects or bounces back off the fish, and the dolphin gets to detect the echo, and the dolphin can tell based on detecting the detected echo. So the dolphin will know how far away the fish are because of the pulse that it sent out and the difference in time when it got back, and they'll be able to figure that out, which is quite amazing. See you on the other side again. Okay, so once again guys, what you see here is a graph or a table. So like I said, do not answer the question. Have a look at the graph, have a look at the units, have a look at what's showing, and then answer the question. Now, in order to answer this question, we need to know something. Number one, this is the amplitude, so it's from rest to peak or from rest to a trough. That's what an amplitude is. Next one, from one place to the same place on the next wave, that's called the wavelength. And so this question is really about the amplitude. And what you need to know for sound, so I'm not talking about EMS, I'm talking about sound, right? An amplitude is the measure of how loud a sound is. So if you look here, the amplitude is increasing and the distance from the source is increasing. If you look here, infrasound, the amplitude doesn't decrease that much. So that means your sound's going to be loud over a great distance. This audible one, right, the sound decreases quite a lot with an increasing distance. Whereas with the ultrasound, this is the biggest decrease in amplitude. So it's going to be the quietest the more the distance increases. So that's no good. So the best one is the infrasound. Why? Because the amplitude or the loudness decreases the least over the greatest distance. So that's the answer to that question. And this one here is about earthquakes. So straight away, you know that the answer is going to be seismic waves. Okay. No such thing as volcanic waves, I don't think. And tectonic waves. Like, what are you on about? What are you on about? Anyway, see ya on the next side.